Lesson: Optimization of training processes. Optimizing the training processes in artificial intelligence is crucial for enhancing performance, reducing costs, and achieving faster results. This lesson focuses on actionable insights, practical tools, and step-by-step applications that AI professionals can implement directly to optimize their training processes. Training optimization not only involves algorithmic enhancements, but also requires strategic planning and execution, leveraging frameworks and tools designed to address specific challenges in real-world scenarios. One of the most important aspects of optimizing AI training is the selection of appropriate training data. The quality and quantity of training data significantly influence the performance of AI models. It is essential to begin with a diverse and representative dataset that accurately reflects the problem space. Data augmentation techniques, such as rotation, scaling, and mirroring, can increase the diversity of the training set without the need for collecting new data, thereby saving time and resources. Furthermore, implementing data cleaning processes, such as removing duplicates and correcting errors, ensures the integrity of the dataset, which is a critical step before training begins. Hyperparameter optimization is another effective strategy for improving training efficiency. Hyperparameters are the external configurations of a model that cannot be learned from the data but have a significant impact on its performance. Techniques such as grid search, random search, and Bayesian optimization are commonly used to find the optimal set of hyperparameters. Bayesian optimization, in particular, has gained popularity due to its efficiency in exploring the hyperparameter space with fewer evaluations. This approach utilizes probabilistic models to predict the performance of various hyperparameter configurations and suggests the most promising ones for further exploration. Transfer learning is a powerful framework that can significantly reduce training time and resources by leveraging pre-trained models. This approach is particularly useful when the target problem has a limited amount of data. By using a model trained on a related task, transfer learning allows AI practitioners to fine-tune the model on their specific dataset, thus accelerating the learning process and potentially improving performance. This technique has been successfully applied in various domains, such as natural language processing and computer vision, demonstrating its versatility and effectiveness in different contexts. Implementing distributed training is another practical approach to optimize AI training processes. Distributed training involves spreading the workload across multiple processors or machines, which can drastically reduce the time required to train large models. Frameworks such as TensorFlow and PyTorch offer native support for distributed training, allowing practitioners to scale their models across nodes seamlessly. A case study by Facebook AI Research demonstrated that using distributed training reduced the ImageNet training time of a ResNet 50 model from 29 hours to just 1 hour, showcasing the potential time savings achieved through this method. Parallel to distributed training, the use of hardware accelerators can enhance the training process. Graphics processing units and tensor processing units are designed to handle the parallel computation required for deep learning tasks efficiently. By offloading computations to these specialized devices, training can be significantly accelerated. For instance, training a deep neural network on an NVIDIA V100 GPU can be up to 10 times faster than using a CPU, providing substantial improvements in training speed and efficiency. Monitoring and evaluation are critical components of training optimization. Effective monitoring allows practitioners to detect issues such as overfitting or underfitting early in the training process. Tools like TensorBoard provide visualizations of model metrics and training progress, helping practitioners make informed decisions about when to stop training, adjust hyperparameters, or implement regularization techniques. Regularization methods, such as dropout and weight decay, can combat overfitting by introducing constraints that prevent the model from becoming too complex, thereby enhancing generalization to new data. One practical example of successful training optimization is Google's BERT model, which utilizes a combination of transfer learning, distributed training, and hardware acceleration to achieve state-of-the-art results in natural language processing tasks. By pre-training the BERT model on a massive corpus and fine-tuning it on specific tasks, Google was able to produce a model that performs exceptionally well across a variety of language understanding benchmarks. Despite these advancements, optimizing training processes is an ongoing challenge that requires continuous experimentation and adaptation. AI practitioners must stay informed about the latest tools, frameworks, and strategies to remain competitive. The adoption of open-source solutions and collaboration within the AI community can drive the development of innovative techniques and facilitate the sharing of best practices. In summary, optimizing AI training processes involves a multifaceted approach that includes data preparation, hyperparameter optimization, transfer learning, distributed training, hardware acceleration, and effective monitoring. By leveraging these strategies, AI professionals can enhance the efficiency and effectiveness of their training processes, leading to improved model performance and reduced resource consumption. The integration of practical tools and frameworks, supported by real-world examples and case studies, provides a comprehensive roadmap for professionals seeking to advance their expertise in AI performance optimization.